All right, chemistry class. This is Mr. Mellinger, and this is your lesson for May the 19th. It's day 60. We only have about 11 more days to go after today in school. So I want you to get assignments in. Go back and get old assignments in. Anything that I've assigned, including the extra credit that happened before April the 27th, you can turn that in for credit. But that's only can only be turned in up until May the 26th, so that's a week from today. So please get going on assignments if you haven't already. So today we're going to continue with states of matter. That is, what determines whether a substance is a solid, like ice, or a liquid, like liquid water, or a vapor or steam, or a gas, like vapor or steam. And we'll talk some more about that. Okay, so this is what's called a phase diagram, and this one's a little bit busy, but the phase diagram is what you see in the black lines you see that look kind of like a Y. That's called a phase diagram, and it tells you at various pressures and temperatures whether a particular substance will be a solid, a liquid, or a gas. So every substance has its own phase diagram, although they're all generally shaped like this one. So the pressure is on the vertical axis, so higher pressure goes up the vertical axis there on the left, and higher temperature goes from left to right along the horizontal axis. So the three states of matter are solid, liquid, gas. A phase diagram shows the state of a substance at a combination of temperature and pressure. The names given to the phase changes are shown in the phase diagram. So we learned these names yesterday, and now you see how they would fit into the phase diagram. So let's say we start at a pressure about midway up, right about where the P is for pressure. So that's a certain pressure. Now let's go from left to right. If you're at a very low temperature, you're way over on the left side of this graph, and let's just say that pressure that you're seeing there is about 1 atmosphere. So it means it's just normal room pressure. So that means at a very low temperature that the substance would be a solid, like ice if it were water. And then as you go from left to right, that means you're increasing the temperature. You're going along the horizontal axis, and you're getting a bigger and bigger temperature. And then eventually as you get to a certain point, you cross the line from a solid to a liquid. That means your ice has melted because the temperature has increased at that pressure. If you keep going to the right, then you pass through liquid, and eventually you get to where you're over where it says vaporization. And that would be where the liquid water has turned to steam or to a vapor. So that's how you would interpret this at a specific pressure. What about at a specific temperature? Well, generally, if you stay at the same temperature, as you decrease the pressure, what happens is there's no air or atmosphere pushing down on the substance. So it's easier for the molecules to escape. That's why water boils at a lower temperature up in the mountains than it does at sea level, because there's less air up in the mountains. There's less atmospheric pressure pushing down on the water, and so it doesn't take as much energy, as much heat for the water molecules to break away and start floating away. So you can boil water instead of 100 degrees centigrade as it is here at sea level. It's more like 95 degrees centigrade, maybe 96 degrees centigrade. So as you go lower and lower on the pressure, it becomes easier for the molecules to escape. As you go higher on the pressure, then they're pushed down, and it's harder for them to escape at a given temperature. So for example, if you look at right where the T is for temperature, just take that point and go straight up. So at first, if you're at that position of T, you're at a very low pressure, down very low on the graph. That means you're going to be a gas. If you keep that temperature the same and continue to go upward on this graph so that you cross over the line right where it says condensation, then you're going to pass into liquid. That's because the higher and higher pressure is going to squeeze the molecules tighter together to make them into a liquid. Okay, so that's how you read this. And I'll give you some exercises where you can determine the state at various combinations of temperature and pressure. All right, for all substances, if we hold the temperature at T2, so I'm giving you a couple of examples similar to what I just did. If you hold the temperature at T2 and increase the pressure from C to D, the substance will condense from a gas to a liquid. So at C it says vapor. So you're keeping the temperature the same. You're not adding any more energy to the molecules, but you're increasing the external pressure on it. You're squeezing those molecules down. So they go from being a vapor at point C to being a liquid at point D. For most substances, if we hold the temperature at T1 and increase the pressure from A to B, so if you have a certain temperature, then at A it's going to be a liquid. If you increase the pressure, though, you keep pushing harder and harder on those molecules, you'll squeeze them even tighter together, and that will get you up to where B is, and that's going to be a solid. So for most substances, if we hold the temperature at T1 and increase the pressure from A to B, the substance will freeze from a liquid to a solid. Higher pressure squeezes molecules into a tighter position and creates a solid. Okay, there's a couple of special points on a phase diagram. The critical point of a phase diagram is the pressure and temperature at which the gas and liquid phases cannot be distinguished from each other. So you'll notice that the line in the upper right comes to an end there, right where the letter D is written in. And that means you put so much, you have so much energy, so much the temperature is so high, so much kinetic energy in the molecules, they don't want to squeeze together, and yet the very high pressure is trying to squeeze them together. So it's kind of like a battle of two strong guys again. We use that metaphor a lot. You have pressure really pushing down on the molecules, but really high temperature trying to tear them apart, break them apart, or apart from each other, I should say. And so that's called a critical point, and you can't distinguish between the gas and the liquid phase. Critical temperature is the highest temperature at which a liquid can exist. So that would be where the critical point is. That would be the temperature at the critical point. The triple point is a pressure and temperature at which the substance exists as a solid, liquid, and gas at the same time. So if you see that point down there with the handwritten letter A, that's the triple point. And if you're right on that point, you're kind of right in the middle ground between solid, liquid, and gas. So if you move even just a little bit in any one of those directions, a little bit to the left, it becomes a solid. A little bit up, it becomes a liquid. A little bit down, it becomes a gas. So it's a temperature and pressure where effectively you have all three at the same time. Okay, molecules with high intermolecular forces are ones that are highly polar. That would be like water molecules, or large nonpolar molecules, and we're going to talk about that some tomorrow. They stick together better, so they have higher critical temperatures than smaller nonpolar molecules. So polar molecules tend to stick together better because they have kind of a magnetism to them. They have a positive end and a negative end, so they stick together better than nonpolar molecules. So highly polar and large nonpolar will stick together better, and they'll have higher boiling points than weakly polar and small nonpolar molecules. So the more polar the molecule, the more it's going to stick to other molecules of its same type, positive to negative, they stick together. And so that means it's harder for them to break apart. So it takes a higher temperature to get them to break apart, more energy, and therefore they have higher boiling points. Okay, so now we're going to compare two different phase diagrams for two common substances for H2O and CO2. So at normal room temperature, which is about 300 degrees Kelvin and 1 atmosphere of pressure. So if we look at point X, water is a liquid. So water is the diagram over on the right, and you can see at point X that the water is a liquid, and that's basically at 1 atmosphere of pressure and 300 degrees. So if you kind of look off to the left, you'll see that the pressure is 1. And if you go down, you'll see the pressure for the water, I'm talking about the water diagram here, is roughly about 300 if you go straight down. For the carbon dioxide, same thing. If you look over to the left, you'll see it's at 1 for carbon dioxide. This is the graph on the left. So if you look to the left of that X, you'll see it's at 1. And if you go straight down, the X is roughly at about 300. So these are the same temperature and pressure for both, and at that temperature and pressure, carbon dioxide is a gas, and of course we know that because we exhale it all the time when we breathe out, so it has to be a gas, whereas water at normal room temperature and pressure is a liquid. Okay, so I'm going to introduce you to the subject of heating curves. We're not going to get too deeply into these, but a heating curve shows the temperature increase or decrease associated with heat added or subtracted for a substance. The curve below is for water at 1 atmosphere. So what you see is you're taking water at normal atmospheric pressure that's in the room you're in right now, and you're starting it off, if you look at the lower left-hand corner, you're starting it off at negative 30 degrees. So you have temperature, in this case, you have temperature on the vertical axis. So you have the water at negative 30, which, as you know, is going to be ice. Anything below 0 degrees is ice. So from 30 up to 0, you're seeing that the temperature is increasing. But as long as it stays below 0, it's going to continue to be ice. So increase the temperature of solid ice up to 0 degrees. Then you see a flat part where it says melting. And that's changing the state from solid to liquid. That is from ice to liquid water. And one thing you notice about that's kind of interesting, it says ice is melting into water. The temperature stays the same at 0 degrees. It doesn't continue to go up. During a phase change, the temperature will stay the same. So that's why the line is flat for a while until all the ice melts. And then once all of the ice has melted and it's all liquid water, then the temperature will continue. You continue to add heat. The temperature will continue to go upward from 0 degrees. So that middle slanted line, it says increase in the temperature of liquid from 0 to 100 degrees. And it will continue to go up. The temperature of the water, this is like you're boiling water on the stove, will continue to go up until it gets to 100 degrees. Then once the water gets to 100 degrees, liquid water can't be more than 100 degrees, because once it hits 100 degrees, the water molecules are going to have enough energy to break away. So while the water is vaporizing, is turning from liquid into steam, you'll notice you have another flat line there. And as the water turns to steam, it stays at 100 degrees. Then once all of the water has been boiled away into steam, assuming that you can continue to heat the steam, which you can if you have a cover over the pan or have it in, say, like a pressure cooker or something, then you can increase the temperature of the vapor up above 100 degrees, and that's that slanted line that's up at the very top. So that's called a heating curve, and it's different for different substances, because different substances have different freezing points and boiling points. And so that is that. Okay, so now we're going to talk about temperature and what it is. Temperature, we gave you the definition earlier. It's the internal kinetic energy of atoms or molecules in a substance. So if you think of that gray as being some metal, some sort of metal, and the molecules inside are just a generic molecule. It's no particular metal. It could be anything. So temperature is how actively the molecules are wiggling inside of an object. So if we put fire down below, if we put heat and start heating that metal, the molecules are going to start wiggling around, and maybe they'll heat up to, maybe that metal will heat up to 40 degrees centigrade. Now over on the other side, we have a metal that's not being heated, and its temperature is maybe just the room temperature, and that's 20 degrees centigrade. So this is what's happening. This is really what temperature is. Temperature is not something that comes out of the metal. It's internal to the metal, or the substance in general, but in this case the metal. And it's how much the molecules are wiggling and jiggling around like that. So the metal on the left has a higher temperature than the one on the right because its molecules have a higher kinetic energy. They're moving more. All right, now what happens if we take the fire away and put a metal bar in between those two pieces of metal? In other words, a thermal conductor, something that will allow heat to pass through it. Most cut metals will do that. So we put a copper bar in between, and what happens then is the heat energy starts to flow from the metal on the left over to the metal on the right. And what you'll notice about the speed of the molecules is they'll eventually equalize to where they're the same. So they're both at 30 degrees. So they're lower than the original temperature of the metal on the left, the box on the left, and they're higher than the original temperature of the box on the right, and they're all moving the same speed, so they have the same kinetic energy. So that's what heat is. Heat is the transfer of energy. Notice that no molecules jumped over from one of the boxes to the other. It's simply the energy that they transferred over through that copper bar. and you ended up with equal temperatures at both of them. So temperature is the internal kinetic energy, how much the molecules are wiggling around inside of even a solid substance like metal. And heat is it's the transfer of energy from an object at a higher temperature to an object at a lower temperature. Just like you can't drop your pencil and have it fly up to the ceiling, it won't fall up, it'll fall down. Similarly, heat always travels from the higher temperature to the lower temperature. That might seem obvious, but there are situations where that might not be obvious. So that's what will happen, and that's an equalization of the heat between them. So at 7 a.m., your hand is warmer than the metal railing outside at the school. So the heat transfers from the higher temperature to the lower temperature. That is from your hand to the metal bar. So your hand has a certain temperature inside of it. Your body temperature is typically around 98 degrees. And that metal bar is pretty cold at 7 in the morning. So your hand is going to be warmer than the metal bar. But that's not heat. That's temperature. Once your hand touches the bar, then you feel the sensation of coldness because the heat is traveling out of your hand, and that's leaving your fingertips or the skin on your hand feeling deprived of heat. And so because the heat's traveling out of your hand, and that would be heat flow, heat flowing from the hotter object to the cooler object. Now, if you go outside at 2 p.m., where the bar is really hot, it's been sitting out in the sun all day, and it's warmer than your hand, so the heat transfers from the higher temperature bar to the lower temperature, your hand. So again, the temperature is internal to the objects. Heat is the transfer of energy between two objects that have different temperatures. So that concludes our lecture for today. I'll give you a kind of a simple little problem set. I'm sorry this got up late on Tuesday. Had some things going on. And I'll try to get your Wednesday and Thursday up quicker, and you'll have everything for this week. So please be in touch with me. We do have our meeting tomorrow on Zoom at 8 o'clock on either Wednesday or Thursday. And you can join me. You get 25 points extra credit just for logging on and saying hi. Just want to know how you're doing and if you're having any issues. So go ahead and join me tomorrow at 8 o'clock, and I hope to see you then.